All right, pretty much everything that I've written here is what I would expect to see in your paper. You don't need to put the box around the answer. Some of the stuff I haven't read, you don't have to put. But this one right here is a PDF. Again, if you want to use the formula for this, go right ahead. The PDF ones, it's not too bad to use the formula, but if you once you get beyond the equal to, it's probably just easier to use the CDF. There's the answer for that one. Here's the answer here. Again, when you have at least 3, you want 3 or more, so you want to get rid of 0 through 2. You don't need to write what I wrote in red, but I would expect to see everything I have written in blue. 3 to 5, this gives me 0 through 5. I want to get rid of 0 through 2, so that's what I get for that one. Equal to 0, right there. More than 5 like tuna, so greater than or equal to 6. So again, what I haven't read, you don't need to do. That's greater than 5 does not include 5, so it's like saying greater than or equal to 6. So you want to subtract everything up to 5. So you get that answer right there. Less than 3 is like less than or equal to 2. There's that answer. And then I forgot to get rid of this one. You probably don't know how to do that one yet. I need to erase that. One of these days I will remember too, because we didn't talk about those things yet. Okay? All right. So we can graph a binomial. We can graph it using the calculator. The calculator basically, there's a couple things you can do here. If you look at the book on page 426, it kind of gives you some instructions here. So I'll show you that here in a second. The formulas too for your mean and standard deviation of a binomial, they are on that formula sheet. They are right there. That's what you had to use for that number 9. But so there's the 2 formulas for the mean and standard deviation. The formulas are only for the binomial. The geometric, which we'll talk about later, has its own formulas. So those are only for the binomial. Don't use them for other distributions. And so what you can do here, you have a couple options here. So you can go to second vars, find binomial PDF, and you can leave the x value blank, and you can hit paste. So if you notice, it doesn't have an x value there, and you can hit, so I'm going to say store, and I'm going to store this in L2, so second number 2. And sorry, I was looking at something, press enter there. So then if I go to my calculator, what it's done is it put those probabilities in there. So if you wanted to, you could come back here and say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that should be all your probabilities. So that was one way you could do it. Alternatively, I'm going to clear that out. You could also be here. I have the black box up here, cursor down here, and I could go to second vars, binom PDF 10 point, and I could tell the calculator that all my x's are in L1, and I hit paste, and it would do the same thing. So either way, it works. So that gives you everything. This is like the PDF of 0, the PDF of 1, so that gives you everything. Because when you create the histogram, you want everything. So you could now go to second y equal, and you could say you wanted to do a histogram, you wanted L1 and L2, and you would hit that zoom 9. Of course, it's going to be a little funky there because it put everything together. So I'm going to go to window. I'm going to change my x scale to 1. My x max, our highest one was 10. I'm just going to go to 11. I don't think our highest probability was bigger than 0.25. If maybe I'm wrong. But then I hit graph. And you can kind of see what it looks like there. So then, and I could change, if you want me to lower that. So instead of making the y minimum negative, I could just make it like negative 0.01 or something. Get rid of all that stuff. So then it goes like that. So essentially all I did here was I just kind of copied it then onto my graph paper like we've done in the past. So this is my number of heads, and this is the probability of X. So again, you can just hit the trace button. The first one, even it says 0 to 1, but this is discrete. You had 0 heads. You didn't have 0.7 heads. So you had 0 heads. So I just put the 0 underneath there. I just scaled the y-axes. So this one only went up. This was real tiny. The next one was a little bit bigger. And you can kind of see it ends up being symmetric. The peaks here, and then the numbers on the other side, it comes down, and it's the same thing. It's just because it's 50-50. So you can take a few minutes and just copy that right now. Just pause the video. When you're tossing a coin 10 times, again, the binomial mean is just n times p. So I have 10. My probability of success is 0.5. That's just formula. So if a coin was tossed 10 times, I would expect about 5 heads, but that may vary by 1.58 heads. Again, just pause the video if you need more time to write things down. I'm trying to make the video shorter. To use the binomial distribution, we require independence. But there's been many situations where it's okay for us to violate that assumption and we'll still get pretty good results. So I'm kind of going back to the math anxiety here. So I said 1 million high school students responded to a survey, and 300,000 stated that they have math anxiety. 3 students are selected at random. If X is the number of students with math anxiety, find the probability X is equal to 3. Is this the binomial setting? Not really. It's not really independent. I technically, if I'm taking a student out, I'm not replacing the student. So I am switching that probability of success. So the probability of the first kid has the math anxiety is that 300,000 out of 1 million. But then the next kid having it, each the numerator and the denominator has gone down by 1. The third kid, the numerator and denominator has now gone down by 2, or another person. So, and I kept a lot of decimal places there for a reason. If I pretended that this was actually binomial, so if I ignored the fact that it really wasn't independent and the probability of success was changing, and if I just said, let's just say it is independent, and let's just use 0.3, I would use PDF, and I would get this answer right here, and obviously if I rounded that, I'd be exactly the same. So they're really not that different. However, and the reason why they're not that different is because of my large population size and the sample as it relates to it. Let's say I go, instead of having 1 million, now I have 10. So again, the idea here is that it's still not binomial. If I have 10 and I take one out, it's clearly going to impact my probability. They're not going to be independent. So again, the first one having the anxiety is 3 out of 10. Down a kid, now you're at 2 out of 9. Down another kid, 1 out of 8. That's your probability. Before we said, when we had, this is the same number we got up here. So in this case, it didn't work. It was very different. And the reason for that is essentially this idea of this 10% condition. So the 10% condition basically tells us that if our sample is less than 10% of our population, so if our sample is less than 10% of our population, then we can kind of treat the individual observations as independent. So in this one right here, when we were doing this one, our n was 3. 3 is much less than 10% of 1 million. In this one, our population, our sample size is still 3, but now our population is 10. We weren't met here. That's why we were not getting very close results. So the idea here is that when that 10% condition has been met, you're going to get pretty accurate results even if your independence is not met. All right, switching gears here a little bit. The idea here, so not everything follows a binomial. There's also something called a geometric setting. So a geometric setting is we perform independent trials of the same random process and record the number of trials it takes to get one success. So it's different because you're trying to look for when you get your first success. On each trial, the probability of success must remain the same. So you still have that p that's remaining the same. The number of trials x that it takes to get a success in a geometric setting is a geometric random variable. And the probability distribution of x is a geometric distribution with a probability of 3, and so on. So if you notice with that one, you're not starting at 0 and you're not stopping at n because there really is no n. My old book used to use this acronym, BITS. It's still binary, so it's either still yes, a success or a failure. You're still independent, and your probability of success is remaining the same. But there's no longer an n. You don't have a fixed number of trials. You're looking for when you get your first success. So this question says here, there are 5 choices on a pop quiz. What's the probability we get our first correct answer on the 4th question? So it just says there's 5 choices on the pop quiz. It doesn't tell you how many questions are on that pop quiz. You don't know if there's 5 questions or 100 questions. All you know is that you're looking for when do you get your first correct. So your first correct on the 4th one, the probability it takes you to the 4th question, that means your first 3 are wrong, but then your last one is correct. So that's the probability you won't see your first correct question until the 4th question. So again, your geometric starts at 1 and it goes all the way up to infinity. You can't have your first correct question on the 0 question. That doesn't make any sense. And we don't know when this one stops. There is a formula for the geometric probability. I'm going to help you derive it here. It is on the AP sheet. There are 2 calculator commands. I have them listed down below. So again, let's say we have 5 choices for a pop quiz. What's the probability that we get our first correct on the first question? So that's just going to be 1/5. What's the probability we get our first correct on the second question? So that means our first question was wrong, our second question was correct. What's the probability we get our first question correct on the 3rd one? That means our first 2 were wrong, our last on the 4th one. That means our first 3 were wrong, our last one is correct. So you should kind of notice again a little bit of a pattern here. You can kind of see here that what I'm raising the failure rate to is always 1 less than what I'm looking for. So there was no failure in this one. Sorry, I shouldn't have highlighted over there. And then it's always just times 1/5. So that's kind of what happens here. You have the failure, and then whatever that number is minus 1, and then times the probability of success. There's a PDF command, which is for the equal to. There's a CDF command, which is for the less than or equal to. Like I said, here's that formula. Same formula here. They used X instead of K. It's just a letter. No big deal. They don't give you the calculator commands. You should know those. There's your mean. There's your standard deviation formula. And then if you look at this last page here, if we do the first one here together, when you do these ones here, you're going to make sure you just label the inputs again like we've been doing. So the first one says, so an auto parts seller finds that 1% of every part sold is defective. So that means you don't, again, there's no fixed number of trials here. So the first time I sell a defective part, it's on the 10th part. So that would mean all my first ones, so if I wanted to do this as the formula, the first ones are all successful. So it would just be 0.99 to the 9th. But then the last one, yikes, 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 is a failure. So if I wanted to do that using the formula, that's what it would look like. If I wanted to use it using the calculator command, it's a PDF. That's what it looks like. And again, if you notice here, I have P and X. If you want to write it vertically, that's fine. I just don't think I gave myself a lot of space there. The next one, what's the probability of the first defective part is the first, second, or third part. So you can do like the first one plus the second one plus the third one. You can also use the CDF function here. So CDF, remember, that gives you cumulative. So you can use the CDF to get the answer. Go ahead and try number 2, A and B. And pause the video, unpause it when you're ready. This is a PDF. That's the probability there, greater than 4. So again, mathematically you can prove that the area under this curve is 1. We don't do that in this course, but there's an 11.2% chance a player will need more than 4 games to win. Mean or expected value, I already kind of talked about that. Those are on the formula sheet. The shape. All right. You're always a right skewed distribution. Again, as you go on to infinity, the likelihood of your probability of it taking you that long is going to keep getting smaller. So it's always a right skewed distribution, geometric. So this one right here, it says a local fast food restaurant is running a draw 3, get it free lunch promotion. After each customer orders, a touchscreen displays shows the message, press here to win a free lunch. A computer program then simulates one card being drawn from a standard deck. If the chosen card is a 3, the customer's order is free, otherwise the customer must pay the bill. Let X equals the number of customers it takes to get the first free order on a given day. So the probability of getting a 3, there's 4 3s in a deck, so 4 out of 52. So find the mean, it's 1 over 4 out of 52. I think I switched this problem here. To find the interpretation, to find the standard deviation, I'm just using that formula on the formula sheet. Only the numerators under the square root. It's 12.49. So if they run this lunch program on many days, I would expect the first winner on the 13th customer, but that may vary by 12.5 customers. So it's totally possible that it's the first customer. It also wouldn't be surprising if it take me to the 25th customer. Okay? If you need to rewatch anything, go ahead and rewatch the video.